Okay. So Nathan, can you try, about Faraday's law? Very simple way. Can you explain it? Nathan, can you hear me?
Yes, sir.
Okay. You can try, based on your knowledge about Faraday's law. What does it mean?
So the electromagnetic force is equal to the, I believe it's the number of turns around the coil multiplied by I can't remember the numerator, but the denominator is time, the change in time to get a frequency, I believe.
Okay. So what is the physical meaning of it? Practically, in real life, how do you say that? That's the point I'm trying to talk about. So what is electromagnetic induction? Let's start from there. What is the electromagnetic induction? Okay, so let's say this is a battery. We all know this is positive terminal, negative terminal, okay? And let's say this is 1.5 volt battery connected with that. So this is the coil, right? We all know that. This is the coil. And as soon as this battery is connected like this, then what will happen here? Okay, what will happen here? Current will start passing through it, right? Is it right?
Yes, sir.
Okay. Now, when current is passing through any coil, all right, then what will happen? I mean, current is passing through something. What are the two information you can get from there? So, any conductor or any resistor, when you are allowing current passing through it, then two things will be created from there. What are those two things? Right? When current is passing through it, then electric field will be created first, right? Because electric current is passing through it, right? When electric current is passing, the electric current is passing through it, then electric field will be creating, right? Electric field will be created, right? What is next? When electric field is created, then what will create next? Automatically. Magnetic field, right? This is magnetic field. So what does it mean now? When current is passing through any, the conductor, coil, whatever it is, then two things are created at the same time: electric field and magnetic field. All right, what does it mean, magnetic field? Magnetic field meaning, let's say if you have a magnet, so let's say this is North Pole, this is South Pole, all right, then magnetic field is created, meaning magnetic field line will pass like this, right? Negative terminal to positive terminal, all right? So this is the field. This is the field created like this. This is the magnetic field. And when it is, when current is passing through it, then electric field will be created there too, right? So based on the electric field, magnetic field will be created like this. So this is the first thing you need to remember. The second thing is, if you are putting another coil, right, next to it, let's say another coil, putting next to it, then if you are connecting this one with the galvanometer or voltmeter, let's say voltmeter. Why it is voltmeter? Because the voltmeter will tell you whether EMF is creating the EMF, means it's a voltage, right? So EMF is, symbol is E. It's pretty much voltage. So electromotive force, it is the voltage that is created inside the battery, right? So this is EMF. Now, when you are creating magnetic field because of the electric field, all right, then what will happen? This is called primary coil, this is secondary coil. The secondary coil will develop EMF here automatically. So because of the primary coil, where you have control to attach voltmeter, which is 1.5 volt attached with that, as soon as current starts moving through it, then magnetic field will be created, and because of that magnetic field, the secondary coil will develop voltage there. All right, this phenomenon, this second thing, you are not connecting any voltage or any power supply or anything there, but because of these, the first one, primary coil, secondary coil automatically, create electromotive force. That means voltage will be developed there. This process is called electromagnetic induction. All right, this is called electromagnetic. Why it is electromagnetic? Because the magnetic field, all right, is created EMF, that is called electromagnetic induction. All right, electromagnetic induction. That means EMF created because of the primary coil. And this EMF, all right, that is developed inside the secondary coil, that EMF can be formulated, all right, like this, equal to negative N delta phi B divided by delta T. Delta phi B is called magnetic flux. All right, it's called magnetic flux. Now, what is magnetic flux? We talked about during the lecture time in our previous chapter. So let me try to talk about one more time. Magnetic flux is something like this. So when you have magnetic field, when magnetic field lines, those are passing through somewhere, all right, with a unit area. Let's say this is the one of the, the object with cross-sectional area A. When magnetic field lines are passing like this, all right, how many magnetic lines are passing through this unit area. All right, so magnetic flux, that can be written as number of these lines, number of magnetic lines divided by the area, unit area, that is called magnetic flux. Now, the sign delta is written here, right? So, the sign delta basically is change. When these magnetic lines are changing, let's say, if you have a piece of metal and you are passing like this, the metal you are just slicing on and off, you can do it this way. If you do that, then what will happen? That is called change of magnetic field. All right? So, if you are changing the magnetic field, that means you cutting, slicing, or do any kind of change on this magnetic field lines or magnetic flux, it will develop voltage. All right? So, rate of change of magnetic flux, that means that magnetic flux that is created here, and if you are changing the magnetic flux with time, all right, that is called rate of change of magnetic flux, all right, then electromotive force will be created, which is your second one. So how do you say the change of magnetic flux? So if it is created, if the electricity is passing through it, then it will create a magnet. It's called electromagnet. It is created automatically, all right, it's created a magnet. Let's say North Pole, South Pole. Then when it is created magnet, then because of the magnetic field, all right, this magnet, when it is coming to this field, then that is the change of magnetic field. And when that change is happening, then, all right, electromotive force, E, all right, electromotive force, and that is created here, and that is developed a voltage, right, to the secondary coil. So that is called Faraday's law. So Faraday's law says the rate of change of magnetic flux, which is equal to electromotive force. That means secondary coil will create the electromotive force. Now this N is number of turns. That number of turns could be N equal to 1. If you have one turn, then certain amount of electromotive force will be created. If N equal to, let's say, 5, then more electromotive force will be created there. So number of turns that you have here, that is basically N. Okay? And that N is very big factor. The more turns you have, more EMF will be created there. More voltage will be created there. Alright? So that is called Faraday's law. Alright? So today, basically, we are going to test the Faraday's law. Alright? Faraday's law meaning when you have a magnet, and if that magnet is passing through a coil, that means you are changing the magnetic field, then what will happen? It will develop voltage. For example, if you have a coil, right? Let's say you have a coil like this. All right? If you have a coil like this, now inside the coil, if you are connecting to the voltmeter, because you need to understand how voltage is created, right? So that voltage you can measure with these, but you did not connect with the any kind of current, the power supply or anything. You did not connect it. Just you have a coil and you have a voltmeter. Then if you have a magnet, right? If that magnet is moving through this one, let's say North Pole and South Pole you have, right? Then if you move this magnet towards the right or towards the left direction, that is the meaning that you are cutting the magnetic field. Why? Because magnetic field will be like this, right? So this is the magnetic field. This is the magnetic field. We already talked about that. Now, if you are moving, all right, so it should be like this, basically. Now, if you are moving this magnetic field towards the left or right direction, that means you are cutting the magnetic, the flux, right, that you have. That means there is a change in the magnetic field lines or magnetic flux, and that is why voltage will develop there. Now the question is coming, when this magnetic flux is cutting, then obviously this coil will develop some sort of voltage. When this coil is developing voltage, it is the meaning that current is passing through the coil. When current is passing through the coil, then this coil itself will be considered as another magnet. All right, so two magnets will be created here. One is called electromagnet, all right, it's a north pole, south pole. Another magnet, permanent magnet that you have in your hand. And if you move that magnet, all right, then electromagnet will be created because of the voltage developed to the coil. So two magnets, they are interacting each other. And the field of these two magnets, they are always acting opposite to the direction. So if you have the bar magnet in your hand, whatever the magnetic field direction you have, for example, it is moving north to south, then the magnet that is creating, because of the electromagnet, because of the voltage developed inside it, all right, that magnet will act opposite to the pole of the permanent magnet, all right? That is why they are acting opposite. So if you are moving, if you have a north pole here, south pole there, then what will happen? This magnet will develop south pole here, north pole here. And if you are putting south pole here, north pole there, the opposite direction, then what will happen? This electromagnet will create opposite poles here. And that is why if you are moving this magnet towards the towards the left direction, then you see the galvanometer will show, the galvanometer needle will show towards the negative direction. And if you are doing the opposite, then you will see positive direction. Now the question is coming, if you are moving this magnet, all right, then only voltage will develop there. Now this voltage that you are getting will be increased if you move this magnet faster. All right, if you move the magnet faster, only if you have the motion of the magnet, then only voltage will be developed. Now, if the magnet is moving faster, then more voltage will be created. But again, it will move like this. If you move left direction, right direction, then your current will be developed negative, positive direction. So the needle of the galvanometer will move left, right, positive, negative, negative, positive, depending on which direction the magnet is moving. All right? So that is basically called Faraday's law. That Faraday's law we are going to talk about today, and there are different phenomena that we need to observe. All right? And then we need to explain what is the reason. All right? So that is the lab we are going to talk about today. So let's try to move to the simulation software so that we can see very clearly what's going on here. So this is the Faraday's law experiment, and as I mentioned earlier, this is the coil you have, and this coil is connected to the voltmeter or galvanometer. Now galvanometer, this is the needle you have, and this is the positive direction, this is the negative direction. So this needle will move forward, backward, depending on which pole of the magnet you are entering and which pole you are moving away from this coil. Now the question is, as I mentioned earlier, when this magnet is moving backward and forward, then voltage will develop there. And that voltage, which is showing you the indication positive, negative, this way, and I attached a load. It is kind of resistance. If you are not attaching any resistance to the circuit, then you cannot see how much current is passing through it, right? That's why I attached a light bulb here. And this light bulb will turn on if current is passing through it. If this light bulb will not turn on if no current or no voltage is, passing through it, right? So that's the point. Now in this circuit, look at this, there is no power supply anywhere. right? No power supply anywhere. So if power supply is not here, but as the power supply is not here, that means this light bulb should not turn on because no current inside it, right? So that's the point. But with the help of magnet, we are trying to develop current here using the Faraday's law. Okay, so let's try to manipulate this one, or let's try to play with this setup. So first of all, as I mentioned earlier, that this is the magnet you have. All right, this is the bar magnet, this is North Pole, this is South Pole. And if you want to see the magnetic field lines, so let's see how it looks. Let's look at it. This is the magnetic field. Look at this. This is the magnetic field. So magnetic field lines should be 1, 2, 3. All right, 1, 2, 3. All right, so this is the magnetic field lines. You can see very easily. 1, 2, 3, 1, 2, 3. Now, number of these lines will tell you how strong your magnet is. If you have, let's say, 100 magnetic field lines rather than, these 4 lines, then I would say, the magnet which has 100, magnetic field lines should be a stronger magnet. All right, so this is the way we need to count. So the 4 magnetic field or 3 magnetic field lines you have, that means this magnet should have certain amount of strength. Okay, if that magnetic field lines are increasing, then magnet strength will be increasing. Right, this is the way it works. So when you are entering this magnet anywhere, so that means, what is the magnetic flux again? Magnetic flux meaning how many lines are passing through a certain cross section. How many lines are passing through a certain cross section? Let me try to see this way. Now, if I'm trying to put this magnet inside it, let's see what will happen. All right, so I'm entering this magnet inside it. Then how many magnetic field lines cutting or change? So 1 and 1, right? So basically 1 magnetic field line that is entering, to this coil. That means if the area of this coil is A, then how much magnetic flux should be here? Phi B, which is equal to 1 divided by, let's say, A. A is the cross-sectional area of this, right? So that is the flux. Now, what we are trying to do, if we are trying to move this magnet inside the magnet, look at this, all right? Here, magnetic flux you have 1, 2, 3, 1, 2, 3. Now, you have certain amount of current passing through it. So let's say if I am trying to enter it, so it is staying very far. All right. Now, if I'm approaching this magnet inside the loop, look at the meter. Okay. Look at the meter. Look at the meter. Meter's needle is moving slightly. That means little amount of voltage is developing inside this coil. Okay. So let's try to move it. Did you see that? Slightly more. But as soon as I stopped it, then no voltage is developed here. So voltage developed for time being because rate of change of flux happened, and at that time voltage developed there. All right. Now if I move a little bit more, look at this. More magnetic flux are cutting here. All right. Now if I move a little bit more, look at this. More voltage developed there, and you saw the lights turned on. Right. Now the thing is, as soon as cut of magnetic flux, the rate of change of magnetic flux happen, then voltage will develop. All right. But as soon as you stop moving the magnet, then nothing will happen. No voltage will develop there. Now, let's say you entered it. Let's say we want to move towards the left direction a little bit more. Then what will happen? Let's see. More current produced. Now, more current produced here because more magnetic field lines cut. All right. Now, it is moving towards that direction. So this coil is moving away from this coil. So no current is producing here. That means no voltage is producing here. Voltage is producing, but very little, tiny. Okay. Now, if you move that one towards the right direction, then what will happen? Look at this. Okay, it moves negative direction again, negative direction again, negative direction, positive direction again. Now, negative direction, you saw that, positive direction. But the question is why? When it is moving that direction, that means for time being, the voltage is developed to this circuit. At the same time, current starts flowing. Why current starts flowing? Because as soon as voltage is developed here, current will produce, because you have to have a light bulb which is considered as a resistor. So light bulb will consider as a resistor and current starts flowing through it. All right. When current flowing through it, then what will happen? This coil will develop electromagnet there, and that magnet basically opposes the direction of the this magnetic field. That is why, look at this again. All right. So let's say you are moving here, negative direction, because the magnetic field for this electromagnet and the permanent magnet, they should oppose each other always. So magnetic field which is creating to this coil is opposing to this. So I'm trying to bring the negative terminal to this coil. So negative terminal, that is for sure, but negative polarity will be created by this electromagnet. So negative, all right, will show you negative, okay, because they are opposing. So it will show you negative part. Okay, current will produce towards the negative side. Now, if you are moving away, look at this, it will produces positive sign, because if you are moving away, opposite direction, then what will happen? This electromagnet will create, south polarity. So south polarity, that will show you to the right hand side. So if you are moving this one backward and forward, look at this. This meter is producing, voltage towards the right, towards the left direction. All right. So this is one of the things. Okay. So let's say you are producing this much current here or voltage here. Now I'm trying to move the polarity of these, by using this one. So if you are pressing this one, it will change the polarity automatically. All right, let's do it this one. Look at this, the opposite direction. So look at the direction of the needle. All right, in your voltmeter, negative direction. I'm changing that one, positive direction. So first click, I am putting the south pole, and the south pole will be created here. That means it is giving you positive, the voltage, the indicator will be in positive direction because they are creating positive pole. Again, if I'm changing the polarity, negative, then it will go to the negative direction, right? Positive, negative direction. So negative there, then be negative, they are opposing. So what is the thing I'm trying to talk about here? Because if you are moving any kind of magnet to a coil, it will develop voltage. All right. And if you are moving faster, slower, depending on that, how much voltage will develop, you can get that information. All right. So question is coming, if you are moving up and down rather than moving left and right, then what will happen? Let's see with that one. If you are moving up and down, still it is developing some sort of voltage, right? But ups and downs. As long as magnetic field lines are cutting or bothered or change, then it will develop voltage. Let's try to see another thing. I'm going to remove these magnetic field lines. All right. Let's say I'm putting these. Okay. So certain amount of current is producing here. Okay. So if you are moving this way, if you are moving positive direction, that means right hand side, then this polarity will be positive. If you're moving left hand side, polarity will be negative. Okay. Now, rather than you have just only one coil, if you have two coils, let's see what will happen. If you have two coils, let's say change the polarity. Look at this. What will happen? Right. This is the voltage is developing. Now, if you are showing the, the magnetic field lines, look at this. It is not cutting that much magnetic field. That's why, no magnetic field is creating here. Now, if you are bringing here, look at this, all right? Current is producing this direction. If you are removing this one, now look at this. Positive, negative direction. If you are moving positive, negative direction, so that is gonna produce magnetic field. All right, so basically, what did you learn from here? When you are moving any magnet inside the coil, all right, then two things are happening there. Magnet itself is magnet itself should have magnetic field, and the place, the coil where voltage is developed, that means current is passing, it will create electromagnet there. And these two magnetic field, all right, they are interacting each other. How they are interacting? Electromagnet will oppose the polarity of the magnet. That means the electromagnet, whatever pole is going inside, the electromagnet will always create opposite, or the opposes that pole. Opposes meaning if it is moving negative direction, that means north pole, then it will create north pole. So that they are opposing each other. And if you are putting south pole inside it, then the electromagnet will create, all right, south pole here. So that they are opposing each other. That's why the negative sign you are seeing here, this negative sign is coming because the two magnetic field, they are interacting each other. They are, the electromagnet opposes the pole of the permanent magnet. And these phenomena basically explained by Lenz's law, Lenz. So Lenz, this scientist basically explained this negative sign, and that's why it is called Lenz's law. So what is Lenz's law? Electromagnet, all right, is always opposes the polarity of the permanent magnet, and that is why the negative sign is coming, all right? So that is our Faraday's law, and this Faraday's law basically we are explaining now. And when you are writing the lab report, whatever I explained, all right, and based on that knowledge, you need to perform something, all right? And that performance, step by step, you need to explain. And every experiment, you need to take, screenshot, all right, what you are doing, and take the screenshot, and that screenshot will go to your lab report. Let me try to explain what you need to do for your experiment. So these are certain things you guys need to talk about in your lab report, and you need to do some sort of, some sort of experiment by yourself at home before writing the lab report. Number one, how many ways can you cause induction? All right, how many ways, all right, can you cause induction? All right, explain your methods, all right, citing evidence from the simulation. So how many ways you can cause induction? So what is the meaning of induction? Meaning of induction is how many ways you can create voltage. All right, now you already saw that, all right? How many ways you can create voltage through this coil? 1, 2 ways, right? So when you write the lab report, so you need to answer that question, all right? So 2 ways you can do it. What are those 2 ways? Entering south pole inside it and the north pole inside it. Both ways you can create induction, right? So what you need to do, first, you need to show this way, all right? And this is one method. Then you need to take screenshot, and that should go one method. one picture. That should be the one method. Then what you need to do, change the polarity, all right? And then you say, this is the second method. The method number 1, you can create when you are entering South Pole. Method number 2, when you are entering North Pole, then you can create induction. That means electromagnetic induction can happen based on 2 ways, all right? So that you need to answer that question, and the explanation, you need to, your simulation screenshot, you need to attach to that. This is the way you need to answer that question, and this is your first experiment you need to do. And similar way, sketch 2 different simulation in which light bulbs lights up, all right? Sketch 2 different simulations in which the light bulbs lights up. You saw that, right? So that is you already saw that. So what is the way, what are the different ways, 2 different ways light bulb can lights up? North Pole, South Pole, if you are pressing into, or entering the coil, then it lights up, right? So that you need to do. Indicate the north-south poles of the magnet. So indicate the north-south pole, you guys understand, you have to indicate that. And the direction of its motion, you need to explain that, okay? Which direction is moving? What is the direction of the induced current in each case? You have to mention that, what is the direction of the induced current in each case, okay? So you have to figure it out that way. And then predict what happens to the brightness of the light bulb when the number of turns in the coil is reduced by half, all right? So you have to guess that one. So if the number of turns are getting half, then what will happen with the brightness? Brightness are increasing or brightness are decreasing. So based on the Faraday's law, you need to explain it. Now the second thing is the speed of the magnet remains the same. If the speed of the magnet remains same, then what will happen? All right, so that you need to explain. So speed is a very important factor in this particular case. So if the speed increases, then more voltage will be developed there, more current will be produced there, and light bulb will be brighter. And if the speed is down, then light bulb will be, less brighter, right? If the speed is same, then what will happen? You need to explain it. How does the speed of the magnet affect the brightness of the light bulb? So you need to explain how does the speed of the magnet affect the brightness of the light bulb. So I already explained that. So you need to write it by your own words. Next is using functions in your function machine. Find the example of when the order in which you place the summarize when what does it mean? When the order in which you place them matters. Okay. So try to answer that question. 2 functions in the machine, the Faraday's machine. Find an example of the order in which you place them matters. Okay. So explain that one. And find the different example of when the order does not matter. Okay. So when the order matters or order doesn't matter. So you need to summarize that. And create a function whose output appears unchanged when compared to the inputs. Okay, so these are the these are the experiments, all right, you need to do, and then answer or explain your observation, right? And the reason or observation, you need to write it down. So what you need to do in the data point, the data and results, the data and calculation, that part, you need to write down this question first, and then show the simulation screenshot. And if you have to explain something, you need to explain next, all right? So this is the way you need to write it down or answer the questions with the experiment systematically, one after another. And that should be your data and calculation, whatever it is. So that part. So do you guys understand what I'm trying to say up to this point? Any question or any concern at this point with this?
For the order, I'm not.
Okay.
I don't quite understand that experiment.
Order, which one you are talking about?
I think it was the second to last one.
Uh,
Using two functions in your function machine.
okay. Okay, using two functions, this one, right?
Yes.
Okay. So using two functions in your function machine meaning in the magnet, right? Magnet and coil.
Right.
All right. So two function meaning when you are moving towards the right direction, left direction, that means north direction, north pole, south pole. When you are moving, all right, then find an example of when the order, the order is matter or not. That is the question I'm talking. Order meaning north pole, south pole, north pole, south pole, right? So that order is matter or not.
Okay.
You understand?
Yes, sir.
So that is the thing you need to explain. Okay, so let's say, all right. So order meaning this order is important or not. That is the question I'm asking. All right. So let's say, yeah.
Okay.
So this is the one coil, and if it is two coil, all right. Let's say whatever voltage is developing here, and the number of turns are very important, right? So in this case, two turns you have. Whatever voltage is producing here, look at this maximum voltage, how much maximum voltage you can get here. And the same way, let's say, if you are bringing this magnet here, that is going to give you more voltage because of more turns. 1, 2, 3, 4 turns here, 2 turns here. Now, whatever voltage you are developing here, all right, and whatever voltage you are developing here, they are pretty much half, right? This is half of the voltage you are getting compared to this one. Why? Because number of turns.
Right.
Okay. So that is the thing you need to talk about. And create the function outputs appears unchanged when compared to the inputs. You understand that question, right? So if it is not changing, then what will happen? So with the screenshot simulation data, so you need to explain, right, based on your own way. So what I'm going to do, I'm going to upload this slide to you guys to the Moodle in the lab section. And you guys, when you write the lab report, so as I mentioned earlier, that the challenge prompts, right? So write down the question and try to do something based on the question. And each time you have to take the screenshot and put as a data. And then if you need to explain something, you need to explain based on your way. Then second question, third question, fourth, fifth question, sixth question, systematically you need to write it down and attach your simulation data, simulation in a screenshot, and then explain what you need to explain. And then conclusion, you understand very clearly that conclusion should be, with the Faraday's law experimental setup, we did different experiment and successfully we understood how Faraday's law is working. All right, so that is pretty much very simple conclusion. But the most important thing is your theory. All right, when you write the theory, then you need to explain Faraday's law in details. All right, so what is Faraday's law? And what is the formula for the Faraday's law? And what is the meaning of that negative sign, which is coming from Lenz's law? So all of those things you need to write it down very clearly because most of the points are coming from there. So if you are not explaining properly, then you might lose points, all right? So my advice is when you are writing the theory part, please go to the chapter 19, that Faraday's law and Lenz's law, that part. Please read it carefully and then start writing, all right, the theory. All right, and the material used, you understood, what are the different, Faraday's law experimental setup, what are the different components you have, you need to write it down. I think, you should not have any problem. And what else? Yep, that's it. All right, so objective should be, I hope you guys understand what is objective. Just to prove the Faraday's law. Okay? So that is the pretty much objective. Theory, as I explained earlier, you need to explain Faraday's law, explain the formula and different parameters of the formula, and then explain the Lenz's law, which is the negative sign of the Faraday's law, and what is the meaning of the negative sign, what is the meaning of the Lenz's law, what Lenz's law is telling us, you need to explain. Basically, that's it for the theory. Then material used, then data, and calculations that are pretty much as I explained earlier. And you should not have any graph, so you are fine with that. And then conclusion. All right. And this lab report is due after the break. You already know that. So that lab report is due on July the 9th. All right. And the homework for the lecture, the homework I'm going to upload maybe today or tomorrow. And you guys need to work on during the break and upload on Monday. That should be July the 6th, all right? And July the 7th, when we are coming back, then you have to have your first quiz, right? On chapter 21, all right? Get ready for that. I think that's it. All right, anybody who has a question or any concern at this point? Everybody's okay? All right, so let me take the attendance very quick. All right. Today 6, 25, 20. All right, so that's it for this lab. As I mentioned earlier, that this lab, you should not have any data or graph or anything, just a visual experiment and observations, basically observations and explanation. That's the only thing, okay? So try your best to write the lab report, and I hope everybody should be fine. And today is the last class before the break, so be safe. And if you have any question, even though you are in break, please try to get in touch with me, and I'll try my best to help you guys. Okay. So in terms of anything, if you have a question, you can, try to get in touch with me. All right. So basically, that's it for today. And now, if you have any question, I'll take it. If you don't, then we are done for today. Then. So any question, Nathan?
No, sir.
All right. So Kelsey?
I'm good.
All right, you're fine, right? Okay. Ryan? Okay. Ryan? All right. Chandra? Chandra?
Yeah, I'm good.
You're good? Okay,
Yeah, I'm good.
All right. Kayla, you're fine? Kayla, are you okay? Okay. So it sounds that you guys are okay, but still, if you have difficulties, get in touch with me. I'll try my best to help you. Okay. All right. So as it seems no question, so we are done for today. So see you after the break. That is on July the 7th. Okay. And until then, be safe, stay home, and try to follow the federal guidelines, right? Okay. Thank you.